Good evening, sir. Okay, so we'll begin with our interview session today. One of the most major difficulties in transitioning from higher education to be a research scholar is the unrealistic expectations of what research is supposed to be like. This problem can be easily tackled by listening to the experiences of skillful and successful researchers. A very warm welcome to everyone on behalf of Astronomy Club of IIT Indore. Today we have Dr. Anand Narayanan with us, who is currently a professor in Indian Institute of Space Science and Technology, to share his research work and unique experiences of his research journey and guide us. Thank you, sir, for joining us today.
Professor Anand Narayan has done his B.Tech in Electronics from College of Engineering, Thiruvananthapuram, his MS and Ph.D. in Astronomy from Pennsylvania State University. His research work over the years has involved studying the physical properties of gases outside galaxies in circumgalactic medium and intergalactic space, from distant to the present universe. We are very grateful to have you as a guest of our event today.
Start with the first question right now. I am sure that you will be truly inspiring for all of us who will be listening to this interview. So my first question to you, sir, is that can you brief us about your research area where you're working on right now, and so that you can inspire the other students who want to opt it as a research topic.
Good morning to all the people who are tuning in, and good morning to Soumya and Pranjali, and thanks for inviting me over. So the broad domain of my work falls under this category called extragalactic astronomy, which is studying things that are beyond the confines of our own galaxy, the Milky Way. If you look at the ingredients of our universe is primarily made of ordinary matter, baryonic matter that is made of protons, neutrons, etc., baryons. Then you have two other components which dominate the energy density of our universe, which is dark matter and dark energy. I'm sure many of you who are listening would have heard about dark matter and dark energy. Very little is known about dark matter and dark energy, except that there are multiple lines of evidences that seems to suggest that our universe has these interesting components to it. But when we look at stars, when we look at star clusters, when we look at planets, when we look at our own galaxy, the Milky Way, and other galaxies in our universe, we are actually looking at baryonic matter, which is ordinary matter that is made of protons, neutrons, etc. So this is the directly observable component of our universe. And in my research work, very broadly speaking, in my research work, I have been trying to understand what has happened to these baryons over cosmic time, over the 13 billion year history of our universe. What has happened to these baryons? Where do these baryons reside at different epochs in the history of the universe? What densities and temperatures do they have? What kind of structures are they part of? And then how have these baryons undergone transformation with the formation of galaxies and large-scale structures in our universe? So this is the very broad theme. And as I mentioned, baryonic matter is the directly observable component of our universe. As it turns out, if you focus your studies, if you focus your observations, in astronomy, we don't have experiments. We cannot really tinker with the objects in outer space. All we can do is sit here on Earth and observe them. So you don't say experimental astronomy, it's always observational astronomy. So when we observe, if we confine our observations of the universe to taking just pictures of objects, pictures of stars, pictures of galaxies, etc., then we are only looking at baryons that are emitting electromagnetic radiation, baryons that are emitting light. Now, as it turns out, throughout the history of our universe, from the very early universe to the present, more than 90% of the ordinary matter, the baryonic matter in our universe, has resided outside of galaxies in a very diffuse form where it does not emit any light. So I'm not talking about dark matter, I'm just talking about ordinary matter here. In even that ordinary matter, only 10% of it is in collapsed structures like galaxies, where it is in the present as stars, interstellar medium, planets, etc., that's only 10%. So even though the universe had 13 billion year time period, galaxy formation has been a relatively inefficient process, and only 10% of the cosmic inventory of baryons have gone to form stars, etc., which we can see. 90% is outside of galaxy. So, what in just to put it in an analogy, if we are just studying the universe with the help of pictures, then we are only looking at the tip of the iceberg. So we need to look outside of galaxies in order to be able to understand the baryonic component of the universe. And the way to do this is through some kind of an absorption line spectroscopy method. So in my research work, I have used a technique which is a really efficient and powerful technique called quasar absorption line spectroscopy. The quasar absorption line spectroscopy involves using very distant bright galaxies, which are often commonly referred to as quasars, as background sources to illuminate all the diffuse matter that is present between us and those distant quasars. So when you are looking at a very far away distant galaxy, if you record light from it with the help of a telescope, and if you disperse that light with the help of a spectrograph, you get the spectrum of that object. Now what happens is every parcel of gas that is between us and the distant quasar, those gas clouds will selectively absorb photons from the distant quasar, and so in the spectrum you will see absorption cast by the material that is present in between us and the distant quasar. So we study the diffuse component of the universe by means of the shadow that they cast in the spectrum of background objects. So this is the work that I have been doing for over now 20 years. I have studied many aspects of the diffuse baryons in our universe using the same technique, and for this work I have used ground-based facilities, ground-based observatory facilities, and also space-based facilities like the Hubble Space Telescope and the FUSE ultraviolet satellite. So in a nutshell, this is what my research work is.
I will proceed with the next. So we read in the bio that only about 10% of data. So isn't it counterintuitive that gravity forms filament-like structure instead of planar or spherical boost? Also, can you shed some light on the W model, which accounted for nearly 40% of the baryon that was missing?
Let me just try to answer it in simple terms. So when we map the distribution of galaxies in our universe, when we also map the distribution of ordinary matter in our universe, we find that these galaxies and the large scale structures, they are neither uniformly distributed nor are they randomly distributed. Instead, they seem to arrange themselves in what is known as a cosmic web. Okay, this is very metaphorically referred to as the cosmic web. So there are huge filamentary and sheet-like structures, and where these filaments and sheets intersect, and think of those intersection points as nodes. Those are really overdense regions, and these overdense regions are occupied by large-scale entities like galaxy groups and galaxy clusters. So, and in between these galaxy groups and clusters, they are joined by these bridges of filaments and sheets where ordinary matter exists. Now, this is what we observe, and this is referred to as the cosmic web. So how did this cosmic web structure come into existence? To understand that, we have to rewind back time and look at the very early stages of our universe. By means of electromagnetic radiation, the farthest that we can see corresponds to a time when the universe was roughly 300,000 years old. So that is 300,000 years after the Big Bang. From that point onwards, we get electromagnetic radiation. With gravitational waves, potentially we can even explore earlier time periods. But with the form of photons, this is the furthest that we can see. But the seeds of structure formation, the real reason for structure formation, why the universe has this kind of elementary structure, that corresponds to what was happening in the universe even before this 300,000, which means that we are entering from the realm of observations purely into the realm of theory, okay, where you don't have any direct evidence that this is what has happened, but there are a lot of indirect lines of evidences that seems to suggest that it is what is likely to have happened. So the very early universe after the Big Bang was a sea of ionized particles, so protons, electrons, etc., floating around the plasma state, along with radiation. So it was a sea of matter and radiation. And this sea of matter and radiation had very high temperatures, existed at extremely high temperatures. So most of the matter was ionized. Now, during this time, gravity was trying to pull things close to each other, and this movement was not governed by the gravity between baryons, but it was largely driven by the gravitational force between dark matter. So that is another added layer of complexity. So we will not go into that. But the collapse or the pull was due to gravity. So gravity was trying to pull things close to us together. At the same time, radiation was trying to push things further apart. So matter and radiation were kind of frequently interacting with each other. So you can think of them as two coupled systems. So gravity is trying to pull things closer together, and radiation pressure, the pressure from radiation is trying to resist this coming together. So it's like a competition between two forces, one from gravity and the other from radiation. And so this kind of a collapse and resistance to it, it created oscillations within this baryon photon fluid, the sea of particles and radiation that was present in the universe. It created a kind of oscillation within the sea, and this is called baryonic acoustic oscillation, a BAO for short. So these oscillations kept producing, kept on going for a very some amount of time, and then finally, when as the universe was expanding, it was also cooling down. So the temperature of the universe was going down, and there came a time when, because of the expansion, the radiation temperature had dropped to a value where it could no longer ionize particles. So which means that protons and electrons can find each other and they can form neutral atoms. So once this happened, this is called reionization, recombination. This is called recombination. So once this epoch of recombination happened, then matter and radiation started decoupling from each other, and radiation started free streaming, and matter started forming neutral atoms. So at this point, whatever baryonic acoustic oscillations was existing at that point of time, it kind of froze. Because the purpose of these baryonic acoustic oscillations, or what drove these baryonic acoustic oscillations, was this interplay between gravity trying to bring things together and radiation resisting. But once radiation decoupled from matter, these oscillations kind of froze. So whatever was present in the universe at that time, in terms of regions with high density and regions with low density, that kind of got imprinted as the basic blueprint for structure formation. And then whatever large-scale structure formation that happened based on these overdensities and underdensities that were created at the time of recombination. So those density and fluctuations in the early universe that got frozen with time, those density fluctuations had a certain kind of form which would naturally lead to this kind of elementary structure that we see in the universe. Okay, so what we are seeing as the cosmic web in our present universe is actually a blown up version of the primordial density fluctuations that got frozen in time, roughly about 300,000 years after the Big Bang. So wherever there were regions of higher density, those regions accreted more and more matter, and there galaxies and galaxy clusters formed. And in between those overdense regions, there were wispy density enhancements, and there the other baryonic matter got distributed, and they correspond to the filamentary and sheath-like structure. So this is the basis in a very short description of how the cosmic web structure came into existence. And to answer the latter question of where does warm hot intergalactic medium come into this, so one of the ideas that we get from numerical simulation structure formation is that most of the ordinary matter in our universe, in the present universe, is existing in the form of highly ionized plasma with temperatures of 100,000 Kelvin to 10 million Kelvin. Now, we cannot actually see the universe evolve over cosmic time, so often we have to resort to numerical simulations to understand what has happened to the universe as a function of time. And these simulations say that in the present universe, in the local universe, bulk of the ordinary matter is present in a highly ionized form, and this is called warm-hot intergalactic medium, where warm refers to temperatures of 100,000 Kelvin and hot refers to temperatures of 10 million Kelvin. And this WIM is supposed to be, the short form of warm-hot intergalactic medium is WIM. WIM is supposed to be the reservoir, the repository of large amounts of ordinary matter in our universe. So if you want to do a complete census of where baryonic matter is in the present universe, we need to observe the WIM, we need to detect the WIM.
Going towards the next question, I would like to ask that what was the most interesting topic, interesting area you find in the research which you are doing right now, and you think that more work has to be done?
Yeah, so I kind of answered that question while answering the previous question towards the end. So one of the ongoing efforts, one of the global ongoing efforts in the field of extragalactic astronomy is to complete the census of baryons in our universe. When I say census of baryons, what I mean is have a proper understanding of where ordinary matter is present in our universe. Okay, in what kind of structures ordinary matter is present in, and what kind of densities, temperatures, etc. it has. Now, as it turns out, in the very distant universe, which also corresponds to the very early universe, you may know this, that in astronomy, the further back in space we look, the further back in time we are looking. Okay, so the sky is like a time machine. Every time we look deeper and deeper into the universe, we are actually also looking backwards in time. So when the very distant universe, which also corresponds to the very early universe, the census of baryons is complete. We know exactly where all the baryons that were produced after the Big Bang are present. Now you fast forward it to the present universe, 13 billion years later, which is where we are right now. If you do a census of where the baryons are present, you find that the reservoirs in which these baryons are present are far more complex than what they were in the very distant, in the early universe, the high redshift universe. So doing the census of baryons in the low redshift universe is a huge challenge. It requires very good capabilities, instrumental capabilities. You need a space-based observing platform like the Hubble Space Telescope to be able to do it. Because to discover these baryons, you have to observe the universe at ultraviolet wavelengths, and ultraviolet is not accessible from ground. So you need space-based facilities. And since 2010, and even before that, there has been a large-scale effort from astronomy communities across the world to discover the repositories of these baryons in the low redshift universe. And that census is ongoing, but it is still incomplete. So to answer your question of what is the big excitement is that how soon or how well are we going to fully understand the 4% of our universe, which is what ordinary matter is. The other is understanding how these ordinary matter is organizing itself in the presence of dark matter and dark energy. So dark matter and dark energy are like these, well, at least dark matter is this unseen hand which is molding the formation of structures in our universe. Every large-scale structure that we see in our universe, be it individual galaxies or be it groups of galaxies or clusters of galaxies, they are all being held together by an unseen hand, and that unseen hand is the gravitational potential well created by dark matter. So we know that dark matter aids in structure formation. So to be able to understand how these baryons are tracking the gravitational potential wells created by dark matter is an interesting question. And addressing that requires careful observations and some amount of synergy with numerical simulation. So this is another exciting area of work that's happening. Yeah, so those are some of the things.
So what are the tools and techniques that you have used so far in your work?
Okay, so spectroscopy is the primary tool that we use. See, we all, most of us, when we think of astronomy, we think of these beautiful pictures that we get from space observatories, colorful nebulae, spectacular galaxies, etc. So they are very important. The imaging part of astronomy is very important because it gives us a whole lot of information. But spectroscopy is basically collecting light and dispersing it with the help of some dispersing element like a grating. And so you are sorting the light according to its energy, and that can provide us with a whole lot more information. So imaging combined with spectroscopy provides us with a boatload of information which we can then use to understand, to answer questions, or to do some meaningful work. So imaging has its importance in astronomy, but so is spectroscopy. Through spectroscopy, we can understand the physical properties of systems. For example, what density the particular astrophysical system has, what kind of chemical abundances are present in it. In an astrophysical system, the presence of magnetic fields, pressure, temperature, all these physics quantities we can determine through spectroscopy. So in terms of the tools that I use, for most of my work, I have used a combination of imaging and spectroscopy. Spectroscopy is used to get into the fine details of the astrophysical systems that I'm studying, and imaging helps us to understand the overall morphology of the objects that we are studying. When I say morphology, what I mean is the sizes and shapes of what we are studying. So this is what I have been using, and for this work, I have used data from ground-based facilities like the Keck telescope, which is a 10-meter class telescope on Mauna Kea in Hawaii. I have used data from the VLT, which stands for Very Large Telescope. It's a configuration of 4 different telescopes located in the southern hemisphere in the Atacama Desert in Chile. And I have also used space-based facilities like the Hubble and the FUSE satellite.
Now, little a personal question I would like to ask: that what was the best and worst part of your research journey up till now?
Okay, so see, there are many small discoveries that we have made in our work, but a high point of my own research career was right at the time when I was finishing my PhD. That was the time when the last servicing mission of the Hubble Space Telescope was going to happen. So, as you know, the Hubble Space Telescope is in a low Earth orbit. It orbits around the Earth from an altitude of about 600 kilometers above the sea level. And every few years, so Hubble was launched in 1990, and it's now close to 30 years. And Hubble has been able to provide spectacular science for these 3 decades because every few years, a team of astronauts would go on the space shuttle to do servicing mission on Hubble. So just like we service our vehicles, just like we service things that we use, Hubble also undergoes periodic servicing where they replace some instruments and they repair some broken instruments, and that augments the life of Hubble for several more years. And so in 2009, the last servicing mission of Hubble happened. Okay, after this, there's not going to be any more servicing mission, and that is exactly the time when I was finishing my PhD. And during this last servicing mission, the astronauts who went up into space for a duration of about 7 days, they performed what is known as EVA, extravehicular activity, where they will be tethered, they will be tied to the space telescope, and they will be tied to the space shuttle, and they will float in space, and they will go and do some repair work on Hubble. And one of the things that they did was to install a far ultraviolet spectrograph called Cosmic Origins Spectrograph. It is the short form is COS. And the main science goal, the main science driver of COS was to study the baryons in the low redshift universe, detect baryons in this warm hot intergalactic medium. So I was finishing my PhD with the necessary skills to do this kind of work. And so as soon as I finished PhD, I was offered a postdoc position in the science team of the cosmic origin spectrograph. So I got the chance. I was part of a small team of people who got to look at data from the cosmic origin spectrograph for the very first time before anybody else in the world did. And so we were one of the first to analyze data from COS, and we were one of the first to publish in scientific journals results from the cosmic origins spectrograph. So there was a lot of excitement at that time. There was a lot of promise that COS delivered, and so I was happy to be part of that whole journey.
Thank you for answering that, sir. So the next question will be, what will you suggest to the students who want to make a career?
Yeah, so see, essentially, a career in astrophysics, like any science career, is a long innings. Okay, so you have to be prepared for a long innings. Most people who get employed as astrophysicists, they have a PhD, they have a doctoral degree in this field. So you have to have an interest in higher education. You should be prepared for this long journey. An interest in physics, an interest in mathematics, and a proficiency in computer programming, developing algorithms. These are the kind of skills that we need to become an astronomer. So generally, at least among the public, there is a perception that if you're an astronomer, then your routine includes going out in the night and doing stargazing or looking through a telescope. But that's a great way to engage with the night sky. But professional astronomy is not done that way. Professional astronomy is basically using the fundamental laws of physics, using the principles of physics to understand, to make sense of the physical universe. So it's a way of looking at the world above us through the prism of physics. So a deep interest in physics is important, and if you can build on your foundation of physics, then that is the foundation that you would need if you want to have a career in astrophysics. The future definitely looks very promising. There are many known unknowns in astrophysics. There are many open questions, and there are many facilities that are coming up. There are already coming up, and there are many more facilities that are going to come up both in India and globally to help research in astrophysics. So there are going to be ample opportunities for many people. Just to give you an example, just a few days from now, the James Webb Space Telescope, which is touted as the successor of the Hubble Space Telescope, is going to be launched. JWST is an engineering marvel, and it's going to be another landmark mission in astronomy. It's going to answer many important questions in this in the broader field of astrophysics. So definitely the future looks very fertile, and I think if anybody is interested in this line of work, they should definitely consider seriously about it, keeping in mind that you have to be prepared for this long journey.
My next question to you is, what are the frontier areas in astronomy which are significantly important in current time?
Okay, so I don't know whether I will be able to, I know enough to comment on all frontier areas, but I can tell you about some really exciting developments that have been happening in the field of astrophysics. One is, of course, the discovery of gravitational waves. So gravitational wave astronomy is coming up in a very big way, both in India and elsewhere. So this is a emerging field, and there are going to be many important discoveries that will come in the near future. So gravitational wave astronomy has opened up a new kind of domain within astrophysics called multi-messenger astronomy. And what that means is that for the most part of the history of astrophysics, we have been studying the universe by collecting photons from distant objects. So photons are one kind of messenger particles. So if I want to know some things about the sun, I collect photons from the sun. If I want to know some things about another star, I would collect photons from that star. So photons are these cosmic messengers that help us to understand the universe. Gravitational waves, so photons are electromagnetic radiation. Gravitational waves are completely different. Okay? They are a new kind of messenger, new kind of messenger form in our universe. So, And then we also have fundamental particles, cosmic rays, etc., that provide us with information, neutrinos and things like that. So information not just from the electromagnetic spectrum, but also from gravitational waves and also from high energy particles. These are all being put together to address some common questions, to come up with some coherent ideas about astrophysical objects. So multi-messenger astronomy is emerging as a future. Previously, it was multi-wavelength astronomy. You would study an object in visible wavelength, you would study the same object in ultraviolet, you would study the same object in infrared and in X-rays, and then you will try to put all the information together to come up with the complete description of what that object is. Now we are going even beyond the electromagnetic spectrum. We are even tracking gravitational waves and other high energy particles coming from these different astrophysical objects, if not from all of them. So that is one. The second is, over the last 20-25 years, a field that has been getting a lot of public attention as well as attention within the scientific community is the discovery of extrasolar planets orbiting other stars beyond the confines of our own solar system. And today, prior to 1995, the only planetary system that we knew of was our own solar system. From 1995 till now, in a short span of about 25 years or so, we have discovered more than 4,500 planets orbiting various stars within our own galaxy. And that number is going to just increase as the years go by. And one of the next big steps, so going from discovering extrasolar planets, now we are pushing the frontiers, and now we are asking this question of how many of those planets are Earth-like. In terms of having conditions that are favorable for life. Obviously, we cannot go to those planets because of the enormous distances that separate us from distant stars. So we can do remote sensing, which is sit here on Earth and collect light from those distant worlds and speculate on whether they are potentially safe havens for life. And the next big step in exoplanet studies is going to be the detection of atmospheres of these exoplanets. So from discovering those extrasolar planets, now we are talking about discovering the chemical composition of the atmospheres of these exoplanets. And the reason why the chemical composition of the atmosphere is important is because if a planet has life, then that life is going to affect the environment, the atmosphere of that planet in profound ways. For example, if you take the case of Earth, one of the dominant molecules in Earth's atmosphere is oxygen, molecular oxygen. And we only have very small amounts of CO2 in our atmosphere. If you look at Venus and Mars, the dominant gas is CO2. So how did Earth have an oxygen-rich atmosphere, whereas Venus and Mars have a CO2 atmosphere? And the reason is because in the Earth's atmosphere, the oxygen levels increased after the first life forms originated on Earth. So the life on Earth is what keeps the oxygen abundance on Earth in Earth's atmosphere to very large levels. So discovering similar molecules in exoplanet atmospheres would be an indirect indication that there is a biomass, there is life on those planets. JWST, James Webb Space Telescope, about which I just spoke a couple of minutes back, JWST is going to discover the chemical composition of atmospheres of exoplanets. So that is another big thing. And finally, we do not know what dark matter and dark energy is. We know that dark matter and dark energy put together occupies 96% of the energy density of the universe. There are some working models on what dark matter is and what dark energy is, but we don't have a full description. We don't have a complete description of what it is. So that means, 96% of the universe we do not entirely know. So these are unsolved problems, and they are fields in which a lot of interesting work is happening. So yeah, that's kind of a partial summary of what are the big things happening in the field.
Thank you so much, sir. That was really exciting. I mean, you clearly laid out the fields. It was so. I would like to now move on to the next question. So, what are the qualities according to that a beginner research scholar should develop?
Okay, so yeah, I don't know whether there are any finite set of qualities, but let me split it into two. One is personality and temperament wise, and the other is skill wise. Okay, so personality and temperament wise, patience is very important. Okay? Research work often takes its own time to unfold, especially if you're new to that field. There you need to be a lot patient before you start seeing success, and you have to be careful and systematic in what you do. And everyday work can get a little monotonous. If you talk to research scholars in your own institute, people who are doing PhD, you may find that some of them telling that their work is a bit monotonous. So one important way or one easy way to come out of that monotony is to see the big picture, to constantly remind ourselves of the enormity of what we are doing. Sometimes when we do this nitty-gritty things on a day-to-day basis, we fail to appreciate the fact that we are studying nothing less than the universe. So it's like, if you work for the Space Research Organization, there are thousands of engineers and scientists who are working for Indian Space Research Organization. No one person is designing an entire launch vehicle. It's a collective effort from a lot of people. So if you ask an individual engineer, he or she would be doing a small aspect, which eventually gets integrated into a larger system like a launch vehicle. But this individual person's work might be just maybe measuring the temperature and recording it in an Excel file. The person may have to do it for like months, but somebody has to do it, And so the work can get, at times it can get monotonous, but then you have to remind yourselves that you are part of a bigger canvas. The work that you are doing is going to add essential amount of detail into the ongoing human effort to understand the universe. Hard work is very, very important, and I would say that hard work is probably more important than talent. Okay, some people are gifted with the ability to see through problems and arrive at solutions easily. Okay, so that could be genetic to an extent. So if you have talent, great. That's always wonderful. But you can always, I think, and I have seen examples of this, you can always measure up to talent or even beat talent with hard work. So hard work is extremely important. From skill side, I already mentioned you need to have a fascination for physics. You need to have some interest in mathematics, programming, algorithms. We are living in an age of algorithms. There is big data, there's machine learning, all these things coming into the mainstream of any science discipline. So you need to have a flair for programming. You need to have an interest for programming. Then in general, one should read widely. If you're aspiring for a career in science, it's very important that you read widely, because you never know how or from where you will be able to connect the dots. So reading widely is very important. And also it's good to cultivate abilities to write and speak well. Most of the work that we do, ultimately, you have to present it to people from within your community, and also for the larger cross-section of people who are interested in science, who want to tune into science. So ability to articulate your thoughts, both in the written form and the spoken form, that is also important. So these are, I think, the kind of traits that somebody should have if they foresee for themselves a career in astrophysics or science in general.
Thank you, sir, for enlightening us with that answer. Okay, so my next question is, what are some common difficulties faced by a beginner research scholar, and what strategies did you develop to tackle them?
Yeah, so each person's journey is unique, and each person's journey could be different. So, if I were to think about what are the common issues, as I mentioned, there is a learning curve that is part of any process, and that learning curve can be steeper for some people, and it can be longer for some others. So sometimes steeper can be shorter, and if it is shallower, it can be longer. So you have to be patient. The other is in research, if you were to draw a graph of your emotional state versus time, okay, if you were to draw when you're doing your research, okay, it's going to have lots of peaks and valleys. It's not going to be a straight line. You're not going to have a equilibrium state of mind throughout your journey. There are going to be peaks and valleys. So you can think of these peaks as peaks of ecstasy, when you get success or when things really work your way. And the valleys you can call as valleys of agony, where you feel like there's no end to what you're doing, or there's no light at the end of the tunnel or something like that. So there are going to be huge ups and downs. It is going to be an emotional roller coaster, but that should not deter you, because I think it is common to all creative processes. If you are engaged in any creative process, you are going to go through ups and downs. You ask a filmmaker, a filmmaker's emotional status is not going to be like linear. Okay, you ask an artist, you ask a performing artist. The performing artist is not going to have an equilibrium state of mind. So anybody who is engaged in a creative process, anybody who is walking a path where few others have gone before, you are going to face these ups and downs. Emotional ups and downs is what I'm talking about. But that is part of the package. You sign up for it when you plan for a career in this field, and that is part of the excitement also. And so therefore, initially, when you're starting out, if you feel that there are times when you're overloaded with frustration, etc., you remember that that's part of this process. And there are so many who want to take up science as a career, as a profession, and very few get the opportunities to do that. So having got the opportunity, you can consider yourselves to be in the minority, where you get to choose, you get to study, you get to explore the universe. In the case of astrophysics, explore the universe. In the case of physics, also explore the universe, and also get paid for doing that. Okay, there are very few jobs that will give you that. So yeah, so that's what my advice would be.
Thank you so much, sir. I think it will be very useful for us all. So the last question for this session will be, what do you feel is the research and academic status in India as compared to what's according to your experience?
Yeah, so see, compared to the time when I thought of a career in science to now, so that's a gap of about 20 years or so. If you look at the scenario within India, the academic scenario within India, a huge shift has been at the undergraduate level and also at the postgraduate level. At the undergraduate level, I now see many opportunities for students in India, many avenues for students in India to engage with research, to have an early start on research. So when I look at students in ISERS and I look at students in IIST, IITs, probably this culture was there even well before that. Even in places like NITs and IISc, everywhere you have these integrated BSMS programs where students right after 12th, you are in a program that trains you to become a researcher. That kind of an opportunity was not there 2 decades ago, or maybe a decade and a half ago. So there are many institutes of national importance in the country now. So all these places are going to be excellent avenues for students to start research from a very early age, along with being part of a formal academic training. And in astrophysics, the Indian astronomy community, if I just now come back to just zoom into astrophysics, in astrophysics, the Indian astronomy community is now part of many global campaigns. India is now part of the 30-meter telescope. India is now part of the Square Kilometer Array, SCA, which is a large radio telescope array scheduled for completion in 2024. India is now part of the Global Gravitational Wave Observatory. So India's consortium is called INDIGO, Indian Initiative in Gravitational Wave Observations. Then we are part of many other international level campaigns. So there is a huge thrust now that is now being given into research in basic sciences. It was always there, but I think in the last 20 years or so, that thrust has really increased. So I think the environment, the academic environment, the research environment in India is now very favorable for young people to get into research mode and also get inspired to do enough to think about a career in this field. So yeah, so that's what I think.
Okay, so thank you so much for taking your time over here. And with this, I would like to end this interview session with you.
Yeah, thank you, Pranjali. Thank you, Soumya, for this wonderful set of questions and for organizing this. I'm not sure how useful the answers would be, but I think your editors will do the magic and make it useful. So, thank you.
Sir, thank you so much. Just thanking you is not enough, but still, I mean, we really appreciate the time that you share your experience with us. Any few final that you would like add on before we end the event?
Well, nothing much. I think the future definitely looks very promising for basic research in sciences, whether it is physical science or natural science. I think and there is a lot of opportunities that are there. So I think it's just for all of and whoever is interested to pursue that path. And one of the good things about astrophysics is that it is a universal. It has a universal appeal. And so, even if you're not a professional astronomer, even if you're not academically trained as an astronomer, the night sky is there for all of us, and it doesn't belong to any one particular person. So, even if whatever career paths you choose, whatever fields you end up working in, the sky is always there as a portal to stretch your imagination. So you can always look up into the night sky, and it's a standing invitation to ask big questions. So there are a lot of people who are actively involved in astronomy through stargazing, through education, public outreach activities, who are not professional astronomers. So to be a part of this journey, you don't have to be an academic astrophysicist. Okay, you can be working in any other field and still be a part of this human endeavor. That doesn't mean that you should not aspire for it. I'm just saying that there are many ways to fulfill your dreams.